Bet you can't guess where my company is. Hey, good afternoon. My name's Ian, and welcome to my talk titled Bending Pixels Too Well. Let's talk shaders for all levels. I'm going to try and keep this light and not drown anyone in technical specifics, but if you want to come and talk to me afterwards, I'm more than happy to go into deep dives about stuff as well. So this is how the talk will hopefully go. A quick introduction will be followed by covering what shaders are. Then we'll step through some core-based knowledge for anyone wanting to jump into building shaders. This will cover the use of colours and numbers, UV manipulation, gradient generation, noise, sine and cosine waves, and using existing buffers. Then we'll jump into some fancy tips and tricks, and then wrap up with some questions. So let's start out with the basic who I am. My name is Ian, as I said before, and I have 2 decades of experience working as a programmer. 10 of those years have been in game development. I co-funded an indie game studio called Cloudfire, and we made a game called Starport Delta. I have designed and launched multiple other games, including bespoke titles for big name brands like Jaguar and Wimbledon. I've also worked for a few New Zealand studios like Little Lost Fox, Dinosaur Polo Club, Cinti, and a mystery stealth startup which I can now name as Mission 42. When people ask me how do I describe myself, I tend to answer by calling myself a generalist programmer. But 2 areas that I love to work in specifically are technical design and technical art. The latter is quite handy since this talk today is going to be about doing clever and sometimes deceptively simple things with shaders. But for those of you who are sitting there with quizzical looks on your faces or are just unsure of exactly what a shader is, let's start there. And don't worry, I'll try and keep this talk light, full of pretty images and animations, and I'll try not to overdo the memes, but you can see we're off to a good start. In its most pure form, shaders are just bits of code that are executed on the GPU to transform data at runtime. There are 4 main types of shaders. Vertex shaders, which manipulate vertices to transform or animate objects at the vertex level, and then they're run before geometry shaders, which modify the geo by transforming, duplicating, disregarding things like lines and triangles, and they're run before pixel or fragment shaders, which manipulate individual pixels, applying colours, textures, and other effects. Compute shaders, which are used for general purpose computations, are not normally for rendering, but they are often used for sim calculations like physics or particle systems. In general, shaders are a one-way communication pipeline, with the exception of compute shaders, which means that when you feed the GPU a bunch of instructions, you don't have any feedback returned as to their success. This is one of the reasons shaders are so fast. We're just going to be talking about 2 today, vertex and pixel/fragment shaders. Yes, did that work? No? Hang on. This is always, I'd love to, okay, cool. We'll move on. They will turn something that looks like this in Unity's built-in render pipeline into something that looks a lot more inviting and has motion. Yes, it worked. Or maybe even add some more extreme weather. They'll take a scene that looks like this in Unreal and turn it into something that looks a little more cinematic. Or even take a traditional 3D scene like this using just one post-processing shader. Man, this thing does not like me today. And turn it into a grungy cartoon comic noir style environment. Awesome, well thanks for coming to my talk. Any questions? Nah, just kidding, let's get stuck in. For anyone who read the description of this talk, I made the bold claim that this is going to be a codeless presentation. And by that I mean I will be using common engine material/shader graph editors for all the examples. And that means that you should be able to take the theory behind most of the techniques mentioned today and replicate them in Unity, Unreal, or even Godot. It's worth noting that there are code equivalencies for all of these examples I'm giving in this talk. And those brave enough to venture into HLSL will understand why I'm keeping this talk to shader graphs. But while I did say codeless, I never mentioned mathless. So while I'll attempt to keep the subject matter to a maximum of high school level maths and try not to bore the pants off of you in the process, There might be the odd thing that I touch on that will go a bit beyond that level and dip into specialty knowledge. But I'll do my best to keep things as simple as possible and explain them along the way. Having said that, let's go through some basic knowledge that you'll need if you ever want to jump into the world of shaders. One of the most important concepts to get your head around is the way color information is manipulated. Some of you more adventurous types might have already played around with shader editors before, so you've come across nodes that look like the ones shown. The vertex color nodes are just an example here, but the bits to pay attention to are how those colors are being split out. In all three instances of Unity, Unreal, and Godot in these examples, you're getting the red, green, blue, and alpha channels. In some of these engines they're represented by X, Y, and Z and W. Sorry. But what does this actually mean, and why is it important? Most of the time, when you're dealing with individual color breakouts, they will be trying to map each channel to a 0:1 ratio, where 0 is black and 1 is white. When you combine these values into RG, B, and A channels, it builds a color with some transparency. But what happens if we push these numbers that we're feeding into those different channels past their limits? They'll crush out to either black or white. Now, I feel like I'm going to use this a lot during this talk, but why should you care? You're just keeping the numbers between 0 and 1 most of the time, right? Actually, no. Every time you perform mathematical operations on your colors like adds, subtracts, multiplies, divides, powers, etc., you're actually pushing those numbers constantly outside of the 0 to 1 value range. In this example, let's take our color values we are getting and multiply them by 2. What we're actually doing is changing the overall range of displayable colors by compressing the color range by 2. When the numbers go above 1, they're crushed out to white, but because we're now compressing that range down, it shifts the white crush to start at the original 0.5 value. And I've tried to demonstrate that on this graph. But the differences between the two can be seen a bit easier when shown next to each other. And honestly, it might be a bit tricky to see on a projector, but it'll get more obvious as we go. If we go back to our original unmodified color and instead add 0.5 to it, it has a slightly different effect to the multiply. Instead of compressing the color values, it shifts them. Does anyone know why I suggested adding 0.5 to this example instead of 1 or 2? No? If I had added 1 or 2, since the displayable color range lives between 0 and 1, it would have shifted all the values outside of the color value ranges, and it would just display white. But again, why should you care? These concepts are really important to keep in the back of your head when dealing with things like depth buffers or distance calculation effects. If we created a really simple post-process shader that just grabs the distance from the camera to each object under every pixel, we would just see a white screen. Knowing what we just went through, why is this? Well, because all of the objects in the scene are more than 1 unit away from the camera, any value above 1 crushes out to white. So if we take that distance and divide it by a large number, like 15,000, now we're compressing 15,000 units of distance into the 0 to 1 color range, which means we can now start to see the meshes whose distance from the camera is within 15,000 units. Meshes closer to the camera will appear darker as they have a lower distance value. This is the start of a simple post-process fog. If we simply take that and multiply it with the sampled scene color, then items in the distance will appear whiter than items closer to the camera. While this technique is okay, there are a couple of issues with it. One is that engines like Unreal, post-process materials, when pushed past 1 in the color value range, will start to glow. And this is because the post-process materials in Unreal are driven from the emissive parameter. Instead of multiplying the result, let's go back to our grey distance mask we created earlier and literally use it as a mask. This time, if we use a linear interpolate function, or a lerp, we can feed in our scene color, our desired fog color, and our grayscale 0 to 1 range mask. The lerp function will then fade between the 2 color values supplied, driven by that mask. This effect can be used for all sorts of things like fog, underwater effects, or even hiding unsightly distance LOD pops. For people who have superhuman eyesight and can actually read nodes on the screenshot, but for you guys it should be a bit easier because the screen's so massive, you might notice that there is one called saturate applied to the mask. This is basically a 0 to 1 clamp, meaning any values going beyond the 0 to 1 range will get clamped to either 0 or 1. This is incredibly cheap to use, so anytime you need to apply a quick 0 to 1 value clamp, use a saturate function. Now that we understand how color values operate, let's introduce something into that complexity. Specifically, how numbers work with them. UVs. We should all be familiar with how 3D models are unwrapped using a single texture. So putting aside the thought of multiple UV channels and a light map setups for now, let's just concentrate on channel 0, which in this specific case is our dinosaur's color UV unwrap. UVs work on a 0 to 1 value range. Sound familiar? If you push beyond them though, in the case of UVs, the texture will either repeat or clamp depending on how your shader is defined. In this example, our 0 point is in the bottom left, but this is not the same in every engine. Unity, for example, uses the bottom left as its 0 point, but Unreal and Godot uses the top left as its 0 point, because engines are consistent. Why should you care, though? If you ever have to translate a shader from one engine to another, or if you're looking up an example on how to perform a particular effect or how it's constructed, armed with this information, it will make it much easier to adapt the given example to the engine that you're using. You may have seen these colored squares in UV or texture coordinate nodes in graph editors. As well as being pretty gradients, they actually have a meaning as well. They show you the map of the U and V axis values. These values, if fed into a color data structure, would sit in the first and second values of that structure, which would be red and green. If we look at just the U coordinate, which evaluates to the red color channel, it starts with 0 on the left and moves to 1 on the right. This ends up creating a gradient from left to right across the UV map, which can be extremely handy. Now if we look at the V coordinate, which evaluates the green color channel, it starts with 0 on the top and moves to 1 on the bottom, using the Unreal and Godot standard in this example. This ends up creating a gradient from top to bottom across the UV map, which again is extremely useful. If we take both of those values and put them into a vector 2 format and use the red to represent the X and the green to represent the Y, we get the color gradient we see here. Now, why am I going into great lengths to explain this? Now that you know what the colors are actually representing, you can tell where the origin sits just by looking at the generated gradients. The 0 point is where the gradient transitions to black. Now, remember when I said that generating your own gradients was really useful? Well, you're basically generating a gradient texture without the texture overhead in memory. Whenever you use a texture, that texture gets loaded into memory on the video card, and the more textures you use, the more memory that gets used, the slower things start performing. This starts to get really important when you want to make well-performing games on potato devices, mobile phones, consoles. These kind of devices are normally quite limited on available memory, and so if you start using loads of 4K textures, you're going to find yourself in a pretty bad spot. Or even worse, if your game won't pass the platform requirements because of the memory limitations. So if you can shift some of that texture memory load into some simple GPU-powered math, then the performance games will be worth the effort. You can probably tell I'm excited about gradients, but how useful are they really? Well, let me step you through an example of how we can use them and how cool they can be. We can take a simple gradient generated by the U channel and the texture coordinate and add 0.5 and floor it. This basically says that any value that is less than 1, make 0 and create a hard cut at the 0.5 point on the U axis. Adjusting that input wipes that hard cut backwards and forwards across the gradient. We can make some kind of effect using the same kind of effect using a power with a high input value followed by a saturate. In this example, the power exponent value is set to 500. But here is the cool bit. If you wanted to soften the harsh edge, you can just lower the exponent value of the power. Adjusting the value to 50 creates a much softer edge. Sometimes when using the flawed method, you'll find the edges are quite sharp. The power/saturation combo is the way to mitigate that, and will be something that we touch on a little bit later. Going back to our simple UV-generated gradient, if we use a 1 minus node, which is literally the equivalent of saying 1 minus whatever you're passing into it, we can flip the gradient we've created. Extending this, we can then multiply those inverted gradients on both axes together and then multiply it by a factor to bring the whites back up. And we've created a square soft particle gradient mask with very little memory overhead. Using different blends instead of multiplies also produces different effects. You can combine these different outputs to get some great code-generated masks. For example, if you look at both the darken and difference blends shown here, and then combine them with their equivalent darken or difference blend, you can make some really neat, different gradients. And as a quick bonus note, if you're ever wondering what blends make what sort of gradients, you can find a fantastic resource as part of the docs of a defunct Unity visual shader graph called ShaderForge. The docs are still online, and they're amazing. I can't count the amount of times that I've had to reference this. Now, if we take both of these gradients that we created before and we multiplied them together, you can start to see some quite cool shapes being created. One specifically here that I can see is the shape that is made by the full white color in this result. So if we then ran that through a floor function for the last step, it's starting to look like some leaves that could be used in tree cards, all created with pure shader code, no textures. And by adjusting that multiply factor, we have at the end, we can grow the leaves. If we were to prioritize that multiply factor, parameterize that for, this is why I have notes, parameterize that multiply factor, we could dynamically control how our leaves are grown. Seasonal cartoon tree effects, anyone? In fact, if we can take that lerp, as discussed earlier, and multiply it in the difference blend, this will give us control of the color fade and make it feel a bit more leaf-like. We could keep going with finessing this and adding details computationally, like noise to create rough edges and distortion and sine waves for leaf patterning, and end up somewhere like this. Now, I realize I skipped a bunch of how-to steps here, but this is designed to show you the extremes that you can take it. We are generating all of this purely using numbers, but now imagine if we handed the job of making the gradients to an artist and get them to input that texture. Suddenly, we would be able to have much more curated shaped leaves with random positioning, all growing, turning brown, and dying. But we have to remember the more instructions that we put into a shader, the more costly it becomes to execute. So there's a real balance between saving memory and increasing computational cost. While this is a cool example to look at, realistically, 90% of the effects wouldn't be seen by the player, so wouldn't be worth the computational expense. Welcome to the world of tech art. As you saw with the last additions to the leaf example, noise is probably one of those functions that you'll bump into the most when building different shaders. Noise functions are basically algorithms that generate seemingly random but deterministic outputs. They are a great way of adding randomness to anything, be it textures, effects, or animation offsets. Noise will absolutely become your best friend. The best bang for your performance dollar is going to be texture-based noise. This will either be in the form of a noise generator that uses textures for its generation, or literally a noise texture itself. This will be great news for all of our Godot fans, as Godot's visual shader graph editor is very rudimentary and lacking some functions that engines like Unity and Unreal have out of the box. The flip side of using textural-based noise is that the patterns can emerge when it starts repeating. But often that is masked by the overall effect, and it's so minor that it ends up not getting noticed. When using the non-texture-based generators, it's worth noting that different types of noise have very different performance drawbacks. Voronoi noise, for example, is incredibly helpful for use with water shaders, but is one of the most expensive noises to generate. So again, we're back to deciding where we are happy with our performance bottlenecks being. But why is noise so useful? Let's take a simple circle built from a gradient, a generated radial gradient. This is using a floor function to flatten any of the fractional values down to 0. So keeping that in mind, if we multiply in a noise function before the floor, what happens? We get splotches and fade off towards the edge of the gradient. But why doesn't it cut the noise hard in the shape of the circle that we had before? This comes back to our color range points from earlier. Because we are pushing out our numbers beyond the 0 to 1 range and then flooring, the floor is taking the multiplied numbers and processing them. If we shift the floor function to take place before the multiply on both the noise and the gradient, then the multiply them together, then that will create the cutout effect. However, this previous behavior is actually the neat one that allows us to create some really cool effects. For example, we can take the noise, which currently is generating values between 0 and 1, multiply it by 0.1 to expand the color values, and then add 1, which will shift it right up to the point of crushing out those values. The result is that when the floor finds a value of 1 or above, it clips it to 1. And because we've shifted most of the color values to sit right up at the 1 value range area, it acts as a distortion to the edge of the generated circle. By changing the multiply on the noise, which compresses or expands the value range, we can make the edge noise more or less intense. Before we continue with the edge effect, let's take a quick sidestep to see what happens when we pan and combine noise. We can take the UV coordinates and add a fractional value of time to the U coordinate. This will start panning the noise from right to left across the UVs. If we then take another noise and instead tell this one to pan in the opposite direction and then multiply them both together, we get a mix of noise directional movement. Now, going back to our noise-edged example, supposing we replaced our single noise here with 2 multiplied panning nodes, both moving in opposite directions. We get a really nice liquid edged effect, which can be dialed up or down by adjusting the same multiplier parameter. Again, we can finesse this into a cartoon bubble effect that could be used for a close-up particle system, or just taking the wobbling circular mask, circular mask, shrinking a copy, subtracting one from the other to get the outline. And we can add an offset gradient and another outline calculation, but this time using 2 offset center points to create our fake bubble light reflection at the top. But realistically, this sort of detail probably wouldn't be seen by the player unless they're really, really up close. So balancing performance with visual payoff is important. This kind of effect is used a lot in cartoon water to create animated shorelines just by using the depth fade instead of the radial gradient. Speaking of shorelines and water effects, a set of mathematical functions that you will find incredibly useful are trigonometric functions sine and cosine. This is probably going to be the toughest bit to get your head around if you don't already know what these functions do. So let's try and go through them visually to see how they work and how we can use them. This is the visual representation of numbers that are produced by a sine function. The y-axis on the graph shows what the output will be when you change your x input. Think of this as being a way to smoothly oscillate between values 1 and -1 as your input increases indefinitely. In this example, this sine wave is set to use degrees as a full cycle. Sorry, I've lost my place on my notes. Degrees, so a full cycle of the oscillation occurs every 360 on the x input. If the sine function was using radians, then the 360 value on the x-axis would be 2 times pi instead, or 2 times 3.141592654. I know someone over here can recite it to 100 places, but I'm not going to try that. The reason it uses these numbers is that these trigonometric functions correspond to uniform circular motion, but a lot of the time in shaders they are used to control smooth transitioning between 2 values. So it's important to know if your trigonometric functions use degrees or radians, because this will affect the base speed of your functions if you're plugging time into a sine node, for example. I promise this is going to get more interesting. Hang on. Going back to our sine function graph, it's important to know how to manipulate this graph to do what you want. And there are some very simple rules to follow with it. You can see from the animating box that the values are oscillating smoothly between -1 and +1. We already know from earlier that the values below 0 get crushed to black. This means that it appears to hang on the black color while it's transitioning through the negative values. So this is effectively what our values are doing. But what do we, oh my goodness, I can't read today. What do we do if we want the values to smoothly transition between 0 and 1? Firstly, we start adding 1 to the result of the sine function. This pushes all the values into the positive number space. But now we have the opposite problem. The numbers are clipping when going above 1. We need to bring down the value range by half, so we multiply the result by 0.5. Why not divide this by 2, you ask? Well, there are 2 reasons. The first, division is ever so slightly slower to execute than multiplication in shaders. And the second, if we end up parameterizing a divide value and allow users to enter values that end up being 0, we will get division by 0 errors, which can manifest as bright pink colors appearing out of nowhere in your game builds, which is nobody wants. So I try to avoid using divide operators wherever I can. But now we have a nice smooth oscillation between 0 and 1, which makes this a really nice base to start from, as this sits us right in our perfect color value range. Hey, you know that there's a time remap function, right, Ian? Yeah, I hear what you're saying, there is. And you can use that instead, but it's also very nice to know what it does under the hood. So what happens if we want to speed up the oscillation? Taking the example here, where time is driving the input, we can just multiply time by a factor that will then speed up how fast the sine function cycles between 0 and 1. Okay, seriously, stop. I'm starting to smell stale farts and pencil erasers from my old high school math class. Don't worry, I hear you. So let's just take that graphing goodness and show how it powers some really cool things. Remember that neat growing and dying leaf shader from earlier? Well, that entire shader is driven by using sine function being fed a scaled version of time. In this specific example, Unreal has a neat little extended function called sine remapped, which allows you to feed in the highest and lowest values, and it will map to the sine curve for you, which is really cool. And this is an effect that was created with a couple of offset oscillating sine waves combined with a calculated depth underneath the water mesh. And see this tree sway and twist in this shot? Yep, all driven by sine waves. Now let's move on to something a little less math-based, buffers. Sometimes the engine that you're working with gives you access to a bunch of buffer information that you can tap into in order to create some neat post-processing effects. Let's start with looking at the depth buffers. When an engine wants to work out what objects are rendered in front of others, it uses something called a Z-order, a tool that a number of engines use. Generates a depth buffer, which is a pixel by pixel record of how close or far occluding polygons are away from the camera. This is used to determine which surfaces are visible and which surfaces are hidden by others. We actually made our own kind of similar calculation earlier using the distance between the camera position and the absolute world position. This time, we're going to use the scene depth buffer, which is basically the same thing, but in the form of a texture. We'll perform the same distance scaling as we did with our previous method, but we'll pop a saturate at the end to clamp the color range from 0 to 1. Well, what cool effect can we create with this buffer? Believe it or not, this buffer, along with some other similar buffers, are used to create cartoon outline post-processing effects. There are lots of different ways to create toon outlines, including getting shaders to clone your mesh and invert the normals and set the render Z order to always be behind the mesh that the shader is assigned to, but this ends up doubling up meshes. And I much prefer to build my toon shaders in the post-processing space, as it affords you a little more flexibility when you generate your outlines. It can also sit on top of whatever shaders are assigned to an object, as well as keeping the outline thickness consistent no matter how far away your meshes are. The technique that we're going to use here is to take our scene depth buffer at the top, then subtract a copy, which is then offset by 1 pixel, shown at the bottom. You might now start to understand why we're using the scene depth buffer instead of our previous distance from camera calculation. Because scene depth is a buffer, it's basically a texture rendered to memory and has a UV input, which we can start to manipulate those UVs to create offsets, which you wouldn't have been able to do with the distance from camera method without a lot of extra work. You can see that our outlines are being created, but only on the left side of objects. To fix this, we need to do a bit of copy pasting. We'll take the offset direction, invert it, and then subtract that from the original scene depth buffer to get the outline on the right. We'll then add the 2 subtraction calculations together, and we're starting to get a little more of a toon outline effect. All we need to do is to repeat that process, but instead of shifting on the U offset, we start shifting on the V separately as well. The 2 new subtraction calculations will then be added to the original 2, and we're now seeing much more of an even outline. We can pop a multiply on the offset to help us control our outline thickness and saturate the result. But if we wanted the lines to be overlaid on top of the scene color, we can invert it and then multiply it into the scene color. But this wouldn't allow us to tweak the color and might end up giving us grief in the future. So instead, we'll feed our current mask into a lerp, passing in the desired color for the lines, the scene color, and our black and white mask that we generated. We will then also add a multiply right at the end to add intensity to the lines in case they start to feel like they're a bit hard to see. The end result is pretty nice. However, there are some edges that are getting missed just using this outline edge detection we're implementing here. This is where we can use other buffers to help us out. One buffer that will give us some extra internal line details is the world normal buffer. This buffer uses the calculated normal of each pixel after things like normal maps have been processed and stores that normal direction in the R, G, and B color value channels for each pixel. It creates a pretty funky looking buffer, but we can basically copy paste the same technique that we used in the depth buffer and use it for the world normal buffer as well. There's just a couple of changes needed. Since we aren't dealing with distances any longer, we can remove the 4 divide nodes that were helping us create an inclusion range for our outlines. We also need to desaturate the result and add a power node between it and the multiplier. The power node in this case basically acts as a way to control how much detail is included in the line pass. A value of 2 will start finding a lot more internal lines than a value of 4. It's probably worth noting that the construction of the meshes in this example make a huge difference as to how well the shader works. Cinti assets are a great use case for this because they're low poly, but also have sharp edges for definition, which is this kind of shader picks up on really well. We could really lean into the toon feel with this scene by removing as much of the smooth shading as possible. The diffuse color buffer then renders color without any shading information. We could then feed that buffer into the lerp that applies the lines, but the result is very flat, and like I said before, has 0 lighting information. We can take the current final scene color using post-process input 0 in Unreal, this is all Unreal example, this one, and subtract our diffuse color. This gives us a rough lighting, color, and intensity pass. It's not perfect, but we can manipulate this to give us the equivalent of a shadow pass. Now, it's worth noting that when using deferred lighting, there is no shadow pass that you can just grab like you can with some forward rendering. So we basically have to build our own one. If we desaturate our result, push the color range up using an add, and then power a large number, using a large number, this should start to create a usable shadow pass. The power in this instance, with the exponent sets so high, effectively applies a soft floor if the saturate is used afterwards, like we spoke about earlier. You'll notice that when we used the floor function earlier, that it created some really harsh edges. Using the power with the exponent is a way to soften it. It's a bit more expensive than using a floor, but we're talking by very small amounts. However, if you're using a lot of powers in your shader, then it's time to start swapping some of them out. Now that we have our shadow pass, we can brighten it up with an add. Then multiply it back into diffuse color to apply our recalculated harsh cartoon shadows back into the lerp. The result is pretty good. We have exposed enough parameter values to allow us to tweak this look quite extensively. If we really wanted to be fancy, we could use that same shadow mask to apply another lerp, which would slightly desaturate the colors in the shadows, but keep the colors in the light at full saturation. But let's not get too carried away. To help wind down your brains, or up in some of your cases, let's go through a few one-slide single tips and tricks that will absolutely improve your shader making process and base knowledge. This is the time to get your phones out. 1, put heavy shader logic behind feature switches. Anytime you have complex logic or large collections of functions that make up an effect, put it behind a switch parameter in Unreal or a branch in Unity. Once you create instances of materials that use these shaders, you'll be able to do some fast toggling of chunky features to test performance when benchmarking. But also in Unreal's case specifically, it will help you disable features that aren't needed and save on performance. Don't get confused between these and if statements though. They are very different beasts, and as a general rule, if statements are to be avoided as they are very costly due to their divergent branching and the way your GPU handles parallel execution. Suffice to say, try to avoid using them, and if you have to use them, avoid nesting them at all costs. 2, create material functions or subgraphs instead of your copy-pasting functionality. And I know I was saying copy-paste earlier, but that's just in my example and I can get away with it. Shaders often need repeated actions with slight tweaks to numbers. Instead of copy-pasting your functionality and adjusting the numbers and ending up with spaghetti nightmare that takes you forever to trace through, make use of the material functions in Unity or material functions in Unreal and subgraphs in Unity. These allow you to create your own material nodes with your own sets of logic inside them. Keep your shaders tidy and well presented so others can go in and understand what you're doing. Unfortunately, there is no way to do this yet in Godot's visual shader graph editor, but if you are writing code shaders, then you can create shared code resources and then reuse them using includes. 3, use comment boxes. I mean, this one's pretty obvious, but following on from previous tip, make sure you use comment boxes. These will not only act as informative tools for others looking at your shader, but if you step away and come back to this at any point, remind yourself where you've got to with your shader and what it's doing, and you won't have to spend 20 minutes trying to trace execution lines. I absolutely have not had to do that before. 4, feed noise generators / textures into your UV coordinates for liquid distortion. Because noise generators and noise textures are just spitting out numbers in a range, you can use them to offset your UV coordinates. Panning that noise will then distort that buffer or texture, creating a liquid or water distortion effect. The caveat here is that some versions of Unity will not let you feed texture outputs into the vertex offset, so using generated noise functions here is your workaround. 5, use an object's location to create a random seed. If you're needing a random number to help create variance between your objects, the fastest hack to do this is to grab an object's position, add the X, Y, and Z coordinates together, and that number can then be used for offsetting the time node output to create some pseudo-randomness. This technique works really well for things that are stationary, like trees, rocks, buildings, etc. Obviously, if your objects are moving, you'll need to set up a parameter instead and pass in a random number using C# or Blueprint. But why don't we just use parameters for this effect? Well, there are a couple of reasons. It's more work to set up parameters and then link link to it in code. And more importantly, it comes down to material and shader instances. Using this method, you won't need to generate a bunch of instances for each deviating parameter set. Suffice to say, this way equals more efficiency. 6, use vertex colors for masks. Set up your materials to use the red, green, blue, or alpha channels as a mask for applying effects to your objects. That way, in your modeling program, or in Unreal's case, directly inside the engine, you can paint the mask to have your effect apply to specific parts of the mesh, like I'm doing with the noise in this example, wind noise in this example. Number 7, use depth fade to soften particles. When creating particle shaders, use a depth fade or similar technique to pass or multiply into your opacity to make your particles smoothly fade out when getting near meshes instead of harshly clipping. If you're a Godot user, then there's actually a tick box to do this in the standard particle shader, but if you're writing your own shaders, then this is how the technique works. Finally, number 8, if you're using multiple noise textures or mask textures, combine them into one texture and load it with one texture call rather than 3. It's as expensive loading lots and lots of textures for lower-end devices, so reducing that number is always going to get you a smile from potato users. Sweet performance gains. Hey, congratulations, you've unlocked the hidden bonus content for this talk. It's absolutely nothing to do with the suffering and pain that I've experienced learning Godot after using Unreal and Unity. None at all. So here are some quick Godot visual shader gotchas. For the love of God, take a photo of these slides, if nothing else from this talk, if you're using Godot or planning to start using it. If you're finding that some shader features aren't working the same way as in other engines, that's because Godot splits out its shader types, and you have to use and has to use individual graphs, and can be accessed from the drop-down at the top of the shader window. You can then pass information from the vertex to the fragment or light shader by setting up a thing called a varying. This is basically a variable that's shared across the shader types. Unreal does this automatically and is very much invisibly, where Unity only allows for some information to be shared between the types and then stops you from using anything more than that. Isn't engine consistency great? Speaking of consistency, a lerp, or linear interpolate function, is called, as it's called in both Unity and Unreal, is called mix. Why? Because Godot. Speaking of more jaw-dropping amounts of consistency, if you want to break your vector out into its individual components, in Unity that's called a split, in Unreal it's called a break, and in Godot it's called a decompose. I really hope this is some weird self-reflected foreshadowing of its own internal terminology. After that PTSD-inspired bonus wrap-up, you made it to the end of my talk. Hopefully this talk has given you some good base knowledge and some helpful tips and tricks to get your shaders adventures underway. If you're anything like me, you'll be itching to get home and try out some of these cool things. If you liked the talk and got excited about making some cool things, come and talk to me or anyone wearing these t-shirts afterwards, and we can have a chat about a number of positions available across Mission 42. We're looking for 3D artists, technical artists, anyone interesting, come and talk, you know. We are located in Auckland, and so, you know, if you're interested in joining us, come chat. You know, you can come work with some really, really cool people, like these fellas over here. Yeah. So before I leave you to your own shader discoveries, are there any questions? Cool. I'm just going to point over here. Yeah.
Hey, some really helpful insights. Thank you. I had a question specifically about the if statements in the shader graph. I use those pretty extensively for like custom stencil and Unreal for masking. Do you have any recommendations for alternates that you could use? Yeah,
you can sometimes get away with using lerps instead, because they're effectively, you can turn a clamped mask value into an if, a swapping if condition. But yeah, sometimes it's unavoidable to use if statements if you do try not to nest them. It's just the more nesting you do, the more it ramps up the performance usage of the shader. Yeah.
Awesome, thank you.
Well, that was a really informative talk. Thank you. I was wondering, how do you determine whether to use textures or whether to generate textures computationally or anything like that? In what kind of platforms would are those practices to use textures or generating things in the shader itself?
How do I deal with generating stuff across multiple platforms? Is that what
it's like, it's expensive to use lots of textures because it consumes memory, but it's also computationally expensive to generate things in the shader. So how do you define that? How do you find the balance between the two things?
Yeah, you're welcome to tech art. Tech art is all about finding the balance with what you're working with. And in some cases, it'll be better to use textures, and in some cases, it's better to use generated code. And it completely depends on what your platform is that you're building for and the performance requirements for them. So it's a really hard question to answer without knowing what the platforms that you're referring to are. But yeah, it's a very case-by-case basis, and this is why being a tech artist is so fun.
Hi, great talk. Thank you very much. Just a question on, you seem to favor node-based shaders. Is that because of your background, or do people just not really use code-based shaders as often? Because they're like really wildly complex looking things, like I saw the screenshots.
Yeah, so I chose not to go through code-based shaders because of the complexity behind it, and it's much more absorbable with a visual kind of a visual interface. I do write code shaders and have had to with Godot because their visual graph is awful. They're laughing because they know my pain. Luckily with Godot in specific, you're not actually having to dive into like HLSL. It's still kind of its own flavor of code shader. But I mean, sometimes you can't avoid it. And you certainly can't do things like loops in visual shader graphs, which is why you end up with, like, if you ever have purchased any asset packs from stores and you've gone in to like look at their shader graphs and it just looks like a spaghetti nightmare, that's normally why. Yeah.
Thank you.
Oh no.
Hi. Great talk, thank you. To follow on from that previous question, is there massive performance differences between doing things in a shader graph versus doing things in code, and situations in which you opt for one over the other for that purpose?
Right. Good question. There will be, it's a case-by-case basis. So some shader graphs are really good at compiling down into a nice, like, good code-based shader, and it very much depends on what you're doing. You're always going to be, if you can code if you can code shaders, you're always better off doing it because you can optimize certain things that a visual graph will just miss. So, I mean, I went down the visual graph editor pathway, which helped kind of get into it. But if you need to optimize stuff, you are going to have to dump into code. But you can get away with a lot with a visual shader. But yeah, it's performance is optimizing for performance. You're basically going to have to jump into code. Unreal's pretty good, to be fair. But yeah, there's some weird stuff with Godot and certainly with Unity with how it like. If you've ever dived into how Unity's its new old shader graph editor deals with like its if statements, like sometimes under the hood it actually uses if statements and sometimes under the hood it uses other things, and it will pick when it uses what cases, which sucks because you have no control over how that happens. And that's where you have to basically start going into code shaders. Yeah.
Thank you.
One question here.
Hey, man.
Hey. What's your name again?
I'm Ben. Nice to meet you. Hey, so you mentioned like some docs from a long-dead shader graph plugin for Unity that you use as reference. What are some of the other primary places you go for reference or inspiration? Is it like pulling down Unreal modules and looking at their shaders? Do you go to Digital Foundry? Like, do you have a kind of place to go?
No, that's a good question. For technical reference, it's basically just going for a good internet surf, and there's no real one location. And like certain people, as you use shaders more, you'll start to learn that there are a lot of people out on the internet that do things really badly, and that's fine, because the moment you start to spot that, it means you're good. And but yeah, as far as technicalities go, with stuff like Unreal, you're pulling apart like asset packs and that sort of thing is probably one of the base ones. If you're talking about like visual references, then looking at exactly what you're trying to simulate, and then trying to get your head around the different base components that you can use to produce those effects. And this is why I was going through all of those kind of how to use gradients, how to use sine functions, and all that sort of thing, because a lot of these shaders, they just combine all of this stuff together with some noise and mix it all in a pot, and magic happens. And yeah, it's the best way to figure this stuff out is to play with it, and that's literally the best advice I can give, is to just do it a lot. It's pretty much anything. If you program a lot, you'll get to be a good programmer, and if the more you do, the more you learn. Yeah.
Awesome. Thanks, man. Great talk.
I think you've got two. Oh, we have time?
We got time.
Okay, cool. All right. Well, thank you so much for coming. If you want to chat to me afterwards, happy to talk.